Yes, I'm going to talk about maximum weight online matching with deadlines. This is a joint work with Itai, Max, Chinmoy, Patrick, and Chris. Itai is my colleague at Stanford. Max just graduated from MIT. Patrick is his advisor there, and Chinmoy and Chris are at left. Let me start with two motivating applications. If you place a request for a shared ride on a ride-sharing application like Uber or Lyft, typically the app asks you to wait for some time, in this case for up to 5 minutes. This gives the app a chance to observe the ride request and essentially gives a chance to find more rides that are potentially a good match for you. And it could lead to a better match. On the left-hand side, this is the diagram shows the life expectancy of patients with end-stage kidney disease. These are the patients who go on dialysis. And most of them have around 5 to 10 years. So you have this window to find a match, a kidney for them. I like these two applications because improving the quality of match in the case of kidney matching can lead to improved quality of life or increase in life expectancy. In the case of ride sharing, if you find better matches, you can reduce congestion. And that reduces the time wasted in traffic. So that also leads to improved quality of life. It contributes to the social good. I'm also interested algorithmically because in classic online matching problems or in applications to online advertising, when a new vertex arrives, you have to match it immediately. Here we have a window. We have some time to decide who to match to. And interested to know if that changes the nature of the problem, if it makes the problem easier or harder, or whether we need new algorithms or new techniques. I'm going to tell you about two variations of this model. I'm going to look at the random permutation model and the arrival that's decided by the adversary. Let me start with the random permutation model. So the model is the following. You have a graph of size n. Adversary can choose the weight of the edges, weight of all of the edges. But once the weights are decided, the vertices arrive in a random order. So every time a step, you get a new vertex. The new vertex stays for d steps. And you can match two vertices if they overlap, if they are present at the same time. And your goal is to maximize the expected weight of the matching. Is that clear? So it's like the maximum weight matching in the random order, except that you have this, vertices stay around for d steps.
So is it like matrix?
No, it's a general graph.
The applications were both.
No, in the ride-sharing application, you don't necessarily. It's a carpooling. Yeah, and also in the kidney matching, it's not necessarily a bipartite. So, yeah, but thanks. General graph. The simplest algorithm probably is, I could think of, or the most natural algorithm is the batching algorithm. How does that work? You wait for d plus 1 steps. You get everybody, you look at all the vertices that have arrived. You find the maximum weight matching there. You match them. Then you wait another d plus 1 steps. You will get a whole new set of vertices. You match those, and so on. Now, the question that I have is whether the simple algorithm give you the optimum competitive ratio. Is batching give the best competitive ratio, or maybe even better? Maybe I can find an algorithm that beats this simple algorithm that's widely used. In this talk, I'm not going to give you the answer to this question, because we don't know the answer to the question. We know only this much. We know that the competitive ratio of batching is 0.27, and no algorithm can achieve a competitive ratio better than that. I suspect that at least for large N and D, batching actually gives you competitive ratio of half. We haven't been able to prove it. The fact that no algorithm can achieve a competitive ratio better than half is easy to prove. What I'm going to do is that in the next maybe 10 minutes, maybe 7 minutes now that we started late, I'll tell you about the analysis that drives the 0.27. In fact, hopefully I will be able to give you the highlights of the proof to the extent that you can reconstruct it, the whole thing on your own. All right. So the proof has 3 steps. First, I take this problem, that's analysis of an online algorithm, and we convert it into a graph problem. So it turns into actually a simple graph covering problem. Then I'll show you a few amplification gadgets that they take a proof for a small n and amplify it to a proof for large n, and also take something for a small d and amplify it to large d. Once we know that we have to only focus on a small d, then we can actually use a linear program that captures the factor. It's actually a computer-aided proof. So I'll show you that LP. And before getting to the proof, let me establish some notation. For any graph H, M of H is the value of the maximum weight matching. If I have 2 graphs F and H, the F star H is, if F and H have the same size, is a graph whose edge weights are the product of the edge weights of F and H. Then I have more elementary operations on the graph. Let's say if I add 2 graphs or compare 2 graphs, just imagine I'm looking at the adjacency matrices. So H has the adjacency matrix that's just sum of the 2, or if I say H is bigger than or equal to G, just think about the adjacency matrices. All right. So let's do the reduction to a graph covering problem. So consider this graph. Let's say I order the vertices according to the order of their arrivals. And then for every vertex, I connect it to vertices that arrived up to D steps before and up to D steps after. These are essentially the only vertices that this vertex can be matched to. Now, if I look at this graph and I look at the star of that graph, the operation with the original graph G, when I compute the maximum weight matching here, that will give me the optimum offline. Right? That's essentially an optimum offline. You can look at this range and decide who to match to. Now, the batch algorithm, the support graph is a little bit different because in every DS steps, I look at everybody who's available and find the maximum weight matching. So the support graph is going to look like this. So essentially, the batch collects M of this graph. Let's start with the graph G. Now, I want to compare these two against each other. And if you look at it, you will see that there are some vertices that are connected in the optimum that are not connected here. Maybe 2 vertices that arrive within some distance less than D, but they end up in different batches. But if you look at a different permutation, they may end up in the same batch. So maybe I shouldn't be looking just at this permutation, I should be looking at a collection of permutations. So that's the idea. I'm going to actually look at these batch graphs, and I'm going to take a union of those and try to cover the optimum graph. So I say a set of graphs H1, H2 to Hk is a cover of H if their sum is bigger than or equal to H. Essentially, if their union contains H. I'm going to be also taking linear combinations. So I'm going to take K batching graphs, give them coefficients lambda 1 to lambda K, take at the linear combination. If that's a fractional cover for the optimum under some permutation, let's say identity, then the batch graphs are covering the optimum graph. Therefore, if you look at the maximum weight matching in the optimum graph, it's covered by a collection of matching edges in the batch graphs. So the size of the maximum weight matching in optimum is upper bounded by the sizes of the maximum weight matchings in the linear combination of the maximum weight matchings in batch graphs. So essentially, if I find this cover with some of the lambda k equal to alpha, I have proved that batching is 1 over alpha competitive. The proof is actually a simple change of order in the expectation. All right, now my problem is much simpler. I have this graph that's the optimum graph. I have the batch graphs, and I want to cover the one with linear combinations of the other. So how many copies of the batch graph do I need to cover the optimum graph? Let me show you the 2 gadgets. So imagine you have a cover for a small n. I want to use it to build a cover for large n. And for that, we will use these periodic permutations. So it's actually a little bit easier to look at the cycle instead of a line. So imagine I have a cover for this cycle that's periodic, essentially it's repeating itself, what I can do is that I can open up the cover and then repeat the same pattern. So if I have it for some d and n, I can go to n prime, that's a multiple of d. So essentially, if I have a p periodic permutation, if p divides n and also n divides n prime, I can replicate it, I can expand it. There is another gadget that's essentially cycle contraction. If I have a cycle cover for a small graph, I can repeat every single vertex and get it for a larger graph. So that takes me from a small d to large d. And in both of these amplification gadgets, if you may have a divisibility problem, right? So you may have a large n that's a prime, but then in that case, there is a small rounding error. You have to control for that. So you have a small loss if d does not divide d prime. But the combination of these two gadgets essentially reduce the problem when you have a small d. And then for that, we can write a linear program to find the covering number. Now you can solve it for d up to 50, which is a little bit surprising because if you look at this, it has around 50 factorial constraints here. But you don't really need to sort of look at all the variables and all the constraints. There are some tricks to take advantage of their structure. So essentially, we prove that for d equal to 50, the covering number is less than 3.58. That would give me the competitive ratio that's inverse of that. That's 0.279. So that's what we can get for this problem. Let me tell you a little bit about the adversarial model. So here, again, like before, vertices arrive sequentially and wait for d steps. But now the weight of the edges and also the order of vertices is decided by the adversary. For that, look at the simple application when n is equal to 2 and d is equal to 1. So when d is equal to 1, so you have the first vertex arriving, the second vertex arriving, and you can gain a value of 1. You can wait for the third vertex to arrive, but by that time, the first vertex has departed. So you have to decide whether you're matching the middle vertex to the vertex before or the vertex after without realizing this value of x. If x is significantly less than 1, you want to match right away. If x is much bigger, you want to wait until the last step. And since you don't know the value of x, the best thing you can do is to toss a coin. With probably 50% do one of the two. So that shows you that, one, no algorithm can achieve a competitive factor better than half, and also no deterministic algorithm can achieve any bounded competitive ratio. So essentially, you have to make these decisions of whether you're going to wait until the last minute to get matched, or you're going to be matched to a vertex that's about to depart. You have to make those decisions randomly. So that's actually the first idea of our algorithm. We divide the vertices randomly into two sets, patient versus impatient. Patient vertices get matched until, at the time of departure. So they wait until the last second. Impatient vertices, they get matched to patient vertices when the patient vertices are about to depart. So they get matched before their departure. That's the first idea. The second idea is that if you know which vertices are patient and which vertices are impatient, your problem is relatively simple. It's essentially a maximum weight online matching with free disposal. So there is a factor half competitive algorithm for this problem by Feldman et al. You can also run an ascending auction. So have a primal dual analysis that gives you factor half. There is a third idea. The third idea is that you don't need to make this division of vertices into patient or impatient at the start. You can wait until the last minute. So essentially what we do is that for every vertex we put in two clones. One is patient, the other one is impatient. And we don't decide which one is going to take effect until the vertex is about to leave. Then we toss a coin. We look at the two options, and then we propagate the decision across some alternating path. If you do that, it will improve the competitive ratio a little bit compared to doing it independently. the combination of these three ideas, and I know I did this quickly, shows you that postponed greedy is 1/4 competitive. So these are just two of the results of the paper. You can take a look at the paper for more variations and extensions of this problem. My favorite open problem here is still if batching is half competitive. This is a variation that Ola Svensson suggested, that if you look at the batch of in one word in which you run batch, but every vertex stays for 2 DS steps, versus another word where you can run the optimum algorithm, but every vertex stays for DS steps, can you compare the two? Can you show, for example, batch of 2D plus 1 is better than upper D? Under the adversarial model, we have a lower bound that's, we have an upper bound that's better than half, but still there is a gap between our upper bound and the quarter that I showed you. There are a lot of interesting questions to be asked. For example, if you have vertices that have different sensitivity to weighting, there is a cost to weighting. What do you do there? In general, this interplay, this trade-off of who to match versus when to match, there are a lot of interesting questions to be asked there. There was a paper at EC a few years ago by Akbarpur and co-authors that articulated this question, but under a very simple model. The underlying graph is G and E. If you actually want to solve the optimization problem, you have to look at the breakdown version. And also, in general, look at your favorite online problem and ask this question of what's the trade-off between waiting, making the decision later versus having to make the decision now. Finding out that trade-off. Last spring, I taught a course on matching at Stanford. And one observation that I had was that even though matching and online matching is central and it has several applications, still it's not completely understood. There is a long list of open problems on different versions of the online matching problem where we don't know what the optimum looks like, what the optimum algorithm. I have a long list of problems there. Feel free to come and talk to me and tell you a sample. But for this talk, I'm going to conclude. Thank you.